Welcome once again to my channel. In my previous video, you have seen that the analysis of a diode circuit becomes very simple by using DC modeling technique. Now, what will happen if an AC signal, the small signal, is also present in the circuit? How will you analyze and calculate the voltage and current in the circuit? Will the AC signal affect the load line? Now, the things will not be as simple as in the case where only DC voltage source was applied. That is why in this video, I am going to explain you everything regarding AC analysis and AC modeling of the PN junction diode. To get a better understanding, we will go step by step. In the first step, you will see how AC signal will affect the load line and so the operating point of the PN junction diode. And from the load line analysis, we will model diode as a resistance. This resistance is called the dynamic resistance. So in the next step, we will find out an expression for the dynamic resistance. And also we will know that what factors are going to affect the performance of a diode in the AC analysis. Up to this point, you will know AC modeling concept theoretically. So in the last step, I am going to explain you an example based on this topic. I assure you that after watching this video, you will be able to solve any problem on AC modeling of a PN junction diode. So please watch the video completely and thoroughly, and do not forget to subscribe the channel for more contents. So let's start the topic. This is a simple diode circuit. Here in this circuit, this VDC is the DC voltage. You must be thinking that if we are studying AC modeling or the AC analysis of a diode, then why there is a DC voltage source? See, this is not a mistake. In fact, if we leave some exceptions, then in almost every AC circuit, you will see a DC voltage source. Can you answer it why? You can reply me in the comment section. And VAC is the AC signal, or we can say the small signal. Okay, and we can write this VAC as Vm sine omega t, which means it is a sinusoidal signal, where Vm is the amplitude of this AC signal. Now the net voltage Vt, it will be sum of the DC voltage and this AC voltage, or we can write it as VDC plus Vm sine omega t. So this is a net voltage in the circuit. Here ID is the total current in the circuit. Now let's see how this AC signal is going to affect the load line and so the operating point. Look at this IV graph carefully. You have seen in my previous video that in the DC analysis, this load line VDC-RL and VDC, it will intersect the IV characteristic at some point, and this point is called the operating point and denoted by the letter Q. Okay, Q is quiescent point. Now what will happen when a small signal is superimposed on the DC signal? Then the load line will also runs parallel to that Q point, Q load line. Okay, so when these load lines intersect the IV characteristics at 2 points also, Q1 is corresponding to the point VDC plus Vm and Q2 for VDC minus Vm. We can see that if this Vm value, that is the amplitude of the AC signal, is very small, then the excursion from Q1 to Q2 will also be very small. We can consider this part of the IV characteristic as a straight line. This is called the piecewise linear approximation, or we can say straight line approximation. We are taking Q1, Q2 part of the IV characteristic as a straight line with some slope. So this is the effect of the AC signal on the load line of the PN junction diode. And if this Vm is very small, or you can say the smaller the value of the Vm, the more accurate is our approximation that the part Q1, Q2 is a straight line with some slope. Now in the next step we will understand how we can describe a PN junction diode in AC analysis. As we have seen that Q1, Q2 part of the IV characteristic can be approximated as a straight line, and from Q1 to Q2 the variation in the total current can be represented by del ID. Similarly, the net voltage variation can be represented by del VD. Here we can say that the slope of this straight line is del ID upon del VD. You know this entity? This is a conductance, or we can write it as del VD upon del ID inverse, and this is the resistance. So 1 upon RD and this RD is called as incremental resistance, okay, or we can name it as the dynamic resistance. Why dynamic resistance? Because dynamic means which is variable, varying. Static means which is fixed. So it is varying, that's why del, the differentiating symbol. And if it is incremental resistance, then this GM is called incremental conductance. This means that due to a small signal in the circuit, a diode can behave as a resistance. Therefore, in AC modeling, we can replace a diode with a resistance called the dynamic resistance. But what are the factors which define this dynamic resistance, or the factors which are going to affect the diode performance in the AC analysis? Let's find out. We know that the dynamic resistance is del VD upon del ID. Sorry, this should be small letter and D should be capital. It means this is the net current in the circuit and at the operating point, where this ID at operating point is the sum of the DC current and AC current in the circuit. Let this one be equation 1, so this will be equation 2. And we know that IDQ plus this AC current is IDM sine omega t. So what is this IDQ? IDQ is the DC current which means when VAC is not present in the circuit. So putting or ignoring this VAC in the circuit, you can find out IDQ. So I am writing it directly that IDQ will be VDC minus VD, that is the diode voltage, and upon the resistance, total resistance in the circuit, where if in the problem it is mentioned that diode voltage is the cut-in voltage, then you can write it directly as the cut-in voltage. And R, the resistance, is the sum of the forward resistance plus the load resistance. If forward resistance is not mentioned in the problem, you can directly write it as the resistance is load resistance. Okay, so here this is the IDQ, and to know how it is calculated, go to the link that I have mentioned above. And also from the diode equation, we have the current ID can be written as the saturation current product of exponential the voltage upon the ideality factor product the thermal volt equivalent minus of 1. So let it be equation 4. Okay, now to finding the dynamic resistance, I am differentiating both sides with respect to what? With respect to the voltage. So on differentiating, I will have del ID upon del VD. It is equals to 1 upon eta VT, product of the saturation current and the exponential part, that is the diode voltage eta VT. Not the diode voltage, sorry, it is the voltage in the circuit, the total voltage eta VT. Okay, so this is equation 5. Now the conductance at operating point, we can write it eta VT, and this is IES exponential. Now this voltage will be VDQ upon eta VT. Rest part is same. So, and this is what? This is IDQ. Okay. So, I am writing it directly, eta VT product IDQ. So, this is the conductance part. Now, what will be the dynamic resistance? Just the inverse of it. Dynamic resistance at the operating point is given by eta VT upon IDQ. Okay. So, this is our equation 8. So, as you can see, this is our dynamic resistance, and eta, which is the ideality factor, it varies from 1 to 2, and VT, which is a thermal volt equivalent, it is approximately 26 millivolt, and IDQ. So, this is the current basically which is going to define the dynamic resistance in the circuit, or you can say this current will affect the performance, AC performance of the diode in the circuit. Now let's solve a problem on it. So the question is, the circuit shown in figure is used with this DC voltage, the amplitude of the sinusoidal signal is 0.2 volt, the load resistance, cut-in voltage is given, forward resistance is given, ideality factor is also given. We need to find out the alternating component across the load resistance and the total voltage and current in the circuit. Okay. So, for solving any problem on the AC analysis of a diode circuit, just follow these steps. The first step is draw the DC model. Okay, and from the DC model, find out IDQ. So, let's draw it. We will have only this DC voltage, VDC, then the cut-in voltage, V cut-in, and in series of a resistance, that is the RF, and rest part is same. So, this is our load resistance RL. So, the current in this circuit will be IDQ. You know that the IDQ in this case will be VDC minus V cut-in upon RF plus RL, and everything is given in the problem. So, put the values. IDQ will be equals to 4.18 milliampere. From this IDQ, you can calculate the VDQ. VDQ is IDQ product of RL. Okay. So, now let's see the second step. After finding this IDQ, our second step will be find the dynamic resistance at the operating point, and it is eta VT upon IDQ. Just put the values. You will have approximately 12 ohm. This is the dynamic resistance. Now in the third step, after getting the dynamic resistance, we can draw AC model. Okay, AC model, and from this AC model, well, let's first draw it. So in that case, ignoring the DC voltage and replacing this diode with a dynamic resistance, I am doing in the same figure. So this is RD. Here the current will be purely AC. So finding ID, VAC upon RD, that is dynamic resistance plus the load resistance. So putting the value, so this will be 0.099 sin omega t milliampere. So this is a pure AC current in the circuit. Now from this you can find the pure this net output AC current. So it will be RL upon RD plus RL Vm sin omega t. Okay, from this you can find out this VOC. And in the last step, step 4, using superposition means to find out the net current in the circuit. Okay, so the total current in the circuit is the sum of IDQ and this AC current. So this is ID. The net output voltage at load is V out is ID into RL. This is so simple. You have to just follow these 4 steps and you can solve any problem. Okay, so this is all about the AC modeling of the PN junction diode. In next video, we will study about the Zener diode. Till then, keep practicing. I hope you liked this video. So please press the like button and subscribe and share it also. If you have any queries regarding this topic or any topic on the analog electronic circuit, digital electronics, microprocessors, microcontrollers, embedded systems, VLSI design, you can write me in the comment section or you can mail me. My mail ID is also given in the description of the video. Thank you so much and have a nice day.